everyone. Welcome to SQL Server 2022 Storage Engine Features and Capabilities. My name is David Pless. I'm a Senior SQL Program Manager for Microsoft, covering the SQL Server 2022 release with a particular focus on the new storage engine capabilities, as well as some platform and query store improvements, but my primary focus is the storage engine. Now, we're going to go through a tour of the storage engine scalability improvements. There are so many improvements that will really benefit the larger machines running your larger workloads. We have new capabilities and improvements really that stretch across performance, manageability, and availability. Now, speaking on availability, this is going to be a two-part series. So in this first session, I will be covering the stability and manageability improvements in SQL Server 2022. And my colleague, Kevin Farlee, is going to be covering high availability concepts and new capabilities in SQL Server 2022 with some history of how we got here and your options for building towards an enterprise class availability strategy. Okay, so let's get into the SQL Server 2022 storage engine features and capabilities. So taking an inventory of all the systems you may be maintaining, especially thinking of the life cycle of some of your more critical applications and database solutions, hosting these applications, you may be maintaining any number of SQL Server versions using a number of different features, all in the attempt to properly scale your applications. Now, as data volumes continue to increase, user volumes, workloads increase, your standards also tend to increase. So we need the data retrieved quicker, but we also need the highest availability we can get. So what do we do to improve these standards? Well, DBAs are often put in a position where they have to isolate mission critical databases on specialized hardware. And while features help to improve performance, the data explosion we've seen in recent years demands the highest levels of scalability and the need to maximize the opportunities we have in the copies of our data for optimal business results. Okay, before we get into the feature details around the next release of SQL Server 2022, let's review some of the history from our previous releases. Now, with SQL Server 2016, the tagline is, "It just runs faster." So we had a number of improvements that drove performance. Areas such as improvements with the setup experience and behavioral changes to further optimize TempDB and in-memory OLTP. SQL Server 2016 introduced many foundational capabilities that continues to be improved upon. Query Store is definitely one. It's one of my personal favorites that stores query text, execution plans, performance metrics, all at the database level, making it easier to monitor and troubleshoot, but especially to migrate your databases and upgrade with greatly reduced risk. Additionally, SQL Server 2016 brought a whole new set of security capabilities with always encrypted, dynamic data masking, and row-level security. In SQL Server 2017, it was all about choice, right? So you can run your favorite SQL Server on any Windows or Linux platform, including container images with Docker. And we also started the foundational concept of built-in intelligence with adaptive query processing. The building blocks for intelligent query processing, where simply by making a change of the database compatibility level, you can influence application query plan behavior. We also further improved Query Store by adding the ability to automatically tune a workload by identifying query regression and applying a previously healthier version of the query plan. And in SQL Server 2019, we further improved upon intelligent query processing. And all you had to do, again, is change your compatibility level, in this case to the latest compatibility level in SQL Server 2019, which was 150. We redesigned the database engine recovery process with accelerated database recovery, and we introduced data classification and discovery to SQL Server, making it possible to classify and label sensitive data, allowing DBAs and security admins to meet data privacy standards, and monitor access to highly sensitive data. In SQL Server 2022, along with the Azure integration and security improvements, we have so many other improvements that cut across scalability, manageability, and the availability pillars. In this session, we're going to focus on the scalability and management topics shown here, with some of the management and availability improvements being covered in part two with Kevin Farlee. So let's touch on the performance and scalability improvements in SQL Server 2022. With SQL Server's industry-leading performance, customers can obtain and accelerate query performance with no code changes required with Query Store and intelligent query processing improvements. We touch on some of these improvements here, but for deeper dive on this, on the intelligent query processing improvements, please see the DPS session Intelligent Query Processing Deep Dive on SQL Server 2022 with Kate Smith and Derek Wilson. On top of the performance capabilities with intelligent query processing, there are a number of scalability improvements driving SQL Server to take advantage of the largest systems with the most demanding workloads, with improvements with buffer pool parallel scan, system page latch concurrency enhancements, ordered cluster column store index improvements, improvements with column store segment elimination, and in-memory OLTP improvements. Other improvements include the ability to shrink databases with low priority, XML compression, and more. SQL Server 2022 also has industry-leading availability. So looking at the list of availability improvements, we have always-on availability group improvements that includes contained availability groups, parallel redo enhancements, and improved throughput for distributed availability groups. SQL Server 2022 also comes with integration to Azure SQL Managed Instance, ensuring database uptime with a fully managed disaster recovery solution in the cloud. With link to Azure SQL Managed Instance, organizations can get all the benefits of running a platform as a service environment, but applied to disaster recovery, allowing you to spend a lot less time on setup and management, even when compared to a virtualized IaaS environment. With multi-write replication, SQL Server 2022 enables greater availability with multi-master writes for users across multiple locations with the last writer wins rule. Multiple writable copies of the same database with eventual consistency and automatic conflict resolution with last writer wins. So if a conflict is detected, the most recent modification time will be chosen to be persisted across all the replicas. We also have SQL Server 2022 built-in acceleration that allows DBAs to extend SQL Server Engine with additional capabilities. The accelerator included with SQL Server 2022 is the Intel Quick Assist technology for backup compression that allows customers to offload backup overhead to external devices and also improves software compression algorithms for better backup performance. Additionally, there's accelerated database recovery improvements, enhancing the ADR feature first introduced in SQL Server 2019, greatly improving database recovery. All right, so let's talk about the core storage engine improvements. So here we are going to set the stage for some of the SQL Server 2022 storage engine improvements and features. Some of these are enhancements on existing features, while others are net new options and net new capabilities. So for all of these, system page latch concurrency enhancements, buffer pool parallel scan, in-memory OLTP enhancements, clustered column store indexing improvements, query store enhancements, XML compression, shrink database with low priority, and improved optimization with hardware support. There are some other future deliveries where we're going to discuss and further demonstrate these benefits. So we're definitely excited about these scenarios and sessions. But again, we're setting the stage for SQL Server 2022, and we'll tackle these features in order here today. So let's start with the first one, system page latch concurrency enhancements, the TempDB improvement. I'm going to start with TempDB, but also do a bit of summary on the topic. So first, we know TempDB is one of 4 system databases, and it's incredibly important for SQL Server. You only get one TempDB per SQL Server instance, and TempDB is used by every database for temporary storage. For example, TempDB is used for user objects, such as global or local temporary tables and indexes, stored procedures, table variables, table valued functions, and cursors. But we also use TempDB for internal scenarios, for work tables that store intermediate results, for spools and sorts. There's also hash joins and aggregate operations, and a lot more. So it's important to get SQL Server's TempDB as optimal as possible. We've had best practices on this going back many years to help improve TempDB performance. All using multiple files, all with the same size, using trace flags for uniformity, and to help avoid allocation contention. But even with the best practices being applied, I will have a link at the end of this session just to make sure we're all on target for the best practices. But even with the best practices being applied, we strongly recommend monitoring TempDB using the SysDM OS waiting tasks DMV and older versions of SQL Server, and then starting with SQL Server 2019 using the function sys function page res cracker, which gives us additional details that's helpful for troubleshooting. So the important point here is that SQL Server has improved TempDB in every single release, and SQL Server 2022 is no exception. So, what are the improvements in the previous releases? Well, in SQL Server 2016, the setup itself addressed many of the best practices we recommend rather than DBAs having to correct them after the installation. There are other improvements such as temp tables and table variables being cached to allow operations that drop and create temporary objects to run quicker and to reduce contention. Additionally, when there are multiple TempDB data files, all the files will auto-grow at the same time and by the same amount. So this means that trace flag 1117 is no longer required. Additionally, and depending on growth settings and allocations in TempDB, we will use uniform extents, removing most of the shared global allocation map usage. So this means that trace flag 1118 is no longer needed. And these best practices are now handled for you, and this all started in SQL Server 2016. In SQL Server 2017, we have some internal improvements with the round robin page free space usage. We introduced asynchronous metadata cleanup. We introduced optimistic latching. And also in SQL Server 2017, we increased the initial TempDB file size to allow 256 gigs per file and added the dynamic management view sysdmtran version store space usage to track version store usage per database. Starting in SQL Server 2019, we added the new memory optimized TempDB metadata capability, and we eliminated a lot more of the page free space contention with PFS concurrent updates. And we also brought new installation improvements to Linux. And as I mentioned before, the function sys function page res cracker was added in the SQL Server 2019 release to allow you to quickly diagnose contention rather than having to leverage the SysDM OS waiting task dynamic management view. Now, I still recommend you use SysDM OS waiting tasks for SQL Server versions prior to SQL Server 2019. In SQL Server 2022, we've addressed the other common areas of contention by introducing concurrent GAM and SGAM updates, similar to the concurrent PFS updates. As you know, we use the global allocation map pages when we're looking for uniform extents and the shared global allocation map pages when we're looking for mixed extents in TempDB. And under higher concurrent workloads, we may have GAM contention where many different threads attempt to allocate extents on the same GAM page, and each thread must first wait for another thread to release their update latch before they can obtain the same type of latch to make their changes. So we're just all waiting in line. With the update latch, only one thread can modify the GAM page at a time, and this is what leads us to the contention. And this is also the primary reason we still need multiple data files. So because of this contention, throughput is decreased and workloads that require many updates to the GAM will take longer to complete, while the machine's CPU will be underutilized. This is due to the workload volume and especially the use of repetitive create and drop operations. For the shared global allocation map, though in previous releases we eliminated most of this by using uniformed extents, we can still have SGAM contention where temp tables and table variables will try to allocate from mixed extents. This causes contention when many temp tables are created concurrently. Also, we use the SGAM when we have to address the index allocation map page for the creation of indexes. So with these improvements, we allow concurrent updates to the GAM and SGAM under a shared latch rather than using the update latch. This will also allow parallel threads to be able to modify the GAM page. So the question we often get with SQL Server 2022, if concurrent GAM and concurrent SGAM updates are some of the last areas of contention and we've resolved it, do we still need the best practices? So it's a really good question, and I'll say we don't know. But out of the gate, we're going to continue recommending the same best practices, apply the same approach, but we may adjust if we find that it's no longer required. But in this thought, these questions, an important point should be made that even previously, when we followed the best practices, it may have helped, but it did not completely eliminate the contention. In SQL Server 2022, we are nearly eliminating all of this contention in many ways. So it may change our best practices. Time and testing will tell. Okay, let's take a look at these improvements in action. Okay, I have two machines running. One is a SQL Server 2019 machine, and the other one is a SQL Server 2022 machine. One thing to point out is I'm using the best practices on each machine in exactly the same way. There's 8 files for TempDB, following all the best practices. I have not opted in for the SQL Server 2019 metadata improvement, the hackathon improvement in SQL Server 2019. I have not opted in for that on either SQL Server instance. Okay, so they're exactly the same. SQL Server 2019, SQL Server 2022. Other than the version, we have the same scenario here. Now, what I'm going to do is I'm going to run a workload that is going to drive some contention, some GAM contention on SQL Server 2019 and run the same workload on SQL Server 2022. While I'm doing this, I'm also having a streaming Power BI data set that we can see here. So here I have my SQL Server 2019 machine. Here's my SQL Server 2022 machine. And then I have a streaming data set. This is the streaming data set for SQL Server 2019. And here's a streaming data set for SQL Server 2022. So currently nothing is running on these machines. And I'm going to go ahead and kick it off, the workload, so we can see the difference between the SQL Server 2019 and the SQL Server 2022 performance. So I'm going to go to on the SQL Server 2019 machine, and I'm going to go ahead and kick off this GAM contention workload. And then I'm going to go over to the SQL Server 2022 machine, and I'm going to do the exact same thing. Same scripts, same scenarios. Okay. Now, I'm going to go over to 2019, and you can see here, this is that function page res cracker, the sysdmdb page info. These functions are going to help me get the information I need to see the type of contention I may be having. Remember, as I mentioned previously, I would have used sysdm OS waiting tasks on previous releases of SQL Server. So when I run this script here, let's see if we see anything, and we do. We see it right away. We see that we're getting weights, some page latch weights. And if I'm going to zoom in here, I see that I'm getting page latch weights on 2 is always going to be tempdb. This number here is the file I'm getting the weight on. And this next number here is going to identify the page that I'm having the contention on. So this would be GAM contention. I have a tempdb talk called tempdb the uncontended that goes into a lot more detail about what's going on here. So if you're interested in learning more about contention, definitely check that out. It's the DPS session tempdb the uncontended. So that's basically what you're looking for here in the contention. And you see also here that the page type description is showing that it's GAM contention as well. Okay. Now, I can keep running this to see if things change. Okay, so now it's on the 4th file. The contention's on the 4th file. We see that we have a number of points of contention here, right, at this current time. But what I can do is bounce over to this Power BI data set and see really like what's going on here. And what we see is like a wall of contention. Look at this. So there's almost 180,000 points of contention since I've been running this. Now, I've been running the same workloads per instance. I do this the same way every time, right? So I'll run it on 2019, I'll run it on 2022, or I'll run different type of workloads that cause different levels of contention. And we just passed the 180,000 mark. And we see that the longest wait is almost, well, actually, it's 949 milliseconds. Okay, so just a wall of contention here. Now, let's take a look at SQL Server 2022 and see what we're seeing over there. Okay, we just got one blip on the radar, this. And I can tell you that this would be contention, this would be metadata contention on one of those internal system tables. Had I opted in for the metadata improvement for tempdb and SQL Server 2019, we would have seen nothing here at all. So, and actually, that is the reason why I didn't opt in for that, just so we could be able to have something track and it wouldn't appear that my dashboard is just broken. So, and that, by the way, that is something that you have to opt into. I talk about this more in my tempdb session, but the concurrent GAM and current SGAM improvements in SQL Server 2022 are on by default. So if I go over here, as you would expect, and I run the same script that I did before, man, I'm probably going to just see nothing. And I don't see anything. There's just no contention on SQL Server 2022 as there is on SQL Server 2019 for the scenarios that we have seen here. Okay. So this is what you can expect to see from a performance perspective on SQL Server 2022 in terms of tempdb contention. We've essentially erased it. On SQL Server 2019, I'm going to tell you to use something exactly like this, a script like this, to track the contention scenarios. And you can use the same thing in SQL Server 2022, but for the most part, you're not going to see a whole lot. If you do see something, then you may want to opt in for that metadata improvement that we had as of SQL Server 2019. Okay, so let's move into our next topic. In SQL Server 2019 and previous releases, operations that required scanning the buffer pool could appear to be very slow and taxing, especially on large memory machines such as the M-Series Azure SQL Virtual Machine and larger on-prem SQL Server environments. The impact can be noticed on operations such as creating a new database, backup restore operations, always-on failover events, file drop operations, and DBCC check DB and DBCC check table, and other internal operations such as checkpoints. Customers on these larger memory machines, such as systems with more than 1 terabyte of memory, may witness long database creation operations, and in some cases, it could take several minutes to complete basic tasks. Even log restore operations could be slower, and availability group failover operations can be impacted as well. So, what's our workaround? Well, even in our documentation, we state that there's no way to eliminate this issue prior to SQL Server 2022, and flushing the buffer pool would likely result in some degree of performance degradation, as any subsequent query execution would have to reread data from the database files, increasing the I/O overhead. So you may be wondering, what makes these buffer pool scan operations appear to be slower than expected? The reason for this overhead is that scanning the buffer pool in SQL Server 2019 and earlier releases was always a serial operation. And the larger the machine, the greater the impact. And it really doesn't matter about the size of the operation, the impact can be seen even on creating a new empty database. So it may seem counterintuitive that we would have this issue on a larger machine. I mean, why would a larger machine be slower? Well, it's because of the serial scan process and the larger amounts of memory SQL Server has to address in regards to the buffer pool. In SQL Server 2022, the buffer pool parallel scan feature improves the performance of buffer pool scan operations on large memory machines by utilizing multiple CPU cores. Customers running SQL Server 2022 may see up to a 20 times improvement in executions which were previously slower due to serialized buffer pool scans. The parallel scan feature also improves the buffer pool scan performance of small databases residing on large memory machines. Again, this improvement adds processing power to scan the buffer pool more efficiently, so even small operations on large machines will show a benefit. And this is a general benefit that many customers will witness simply by upgrading to SQL Server 2022. Additionally, you may notice that we have backported the buffer pool scan telemetry for supportability. Long buffer pool scans will be visible in the error log starting with SQL Server 2016 SP3, and more details can be captured using various extended events. In SQL Server 2022, we are adding new extended events for scan, start, and complete, capturing error log events, and flush cache operations for parallel buffer pool events. So customers can already start looking for these events in their current deployments. Even in SQL Server 2016 SP3, we can track long buffer pool scans, so we can start tracking and taking note of how SQL Server 2022 can help improve performance. On the next slide, I have some additional context for these events. As you can see, we've added diagnostics to improve the supportability experience for both serial and parallel buffer pool scans. The events in bold are already available in SQL Server 2016 SP3, and the other events in the debug channel specifically support buffer pool events for SQL Server 2022. The main event to focus on is the buffer pool scan complete event, which is fired when a buffer pool scan takes longer than a second to complete. This event contains the elapsed time, parallel tasks, the number of scanned buffers, the command, and the operation. Additionally, new diagnostics will provide an error log message whenever a buffer pool scan takes longer than 10 seconds to complete. Again, this error log message has been backported and is available starting in SQL Server 2016 SP3. It's a good piece of information to track when you're looking to start collecting data on just one of the many benefits to migrating to SQL Server 2022. All right, let's take a look at a buffer pool parallel scan Azure Data Studio notebook where I did a walkthrough of some of the benefits that you can see with this feature. Okay, so what we're going to do is walk through an Azure Data Studio notebook that's going to compare the performance of a buffer pool scan, a serial scan, what we've seen in prior releases of SQL Server, versus a buffer pool parallel scan. So we know the scenario. This is really going to affect larger memory machines. Think of a terabyte or more, especially like those Azure SQL virtual machines, those M series machines, those really large machines, and certainly those large machines that we have on-prem. And we walked through some of the operations where we can notice this impact. It's actually quite a bit of scenarios, more than folks may think, especially when they have a larger machine. They experience these scenarios. And we mentioned there's no real workaround for this. So this being a feature that's on by default in SQL Server 2022 is just going to be a general benefit that customers have. And you're going to see a lot of performance improvements because of this. And it's going to be very easy to see as we start walking through some of these examples here. Okay, so for this machine, this machine in particular that I ran this against, it's a machine that has 2 terabytes of memory that is on the physical box, and I've got 1.8 terabytes devoted to the buffer pool. Okay, and we can see that here looking at the max server memory. Okay, and what I've done is I've taken a large database. This database is about just over a terabyte, and I've run a stored procedure, created a stored procedure, and run the stored procedure that's going to populate a terabyte of database pages into the buffer pool. Okay, and when we can see this here by running a query against System OS performance counters, and we can see that the database page cache has just over a terabyte of memory, so in the buffer pool. Okay, so we've created this scenario, and now we're going to run through some operations comparing a serial scan for the buffer pool to a parallel scan for the buffer pool. And we're going to do this by using a trace flag to turn the parallel scan off and then turn it back on, and then we'll compare the numbers. Okay. So in the first example, all we're doing is, well, one, we're going to turn the buffer pool parallel scan feature off. And all we're doing is creating a small database, creating a table, and just populating it with some data. And we can see with the serial scan, it takes about 10 seconds to complete this operation. But if we have a buffer pool parallel scan in SQL Server 2022, it's just a second, right? So the comparison here, it's nearly a 90% improvement from the serial to the parallel scan. Another example, and let's look at a maintenance situation, DBCC checkDB and checktable. So I've run DBCC checkDB on 2 smaller databases, then a larger database, ran that 3 times, and then a checktable on a couple of tables. Okay, that scenario took 37 minutes to run on a serial scan, but on a buffer pool parallel scan, it took 26 minutes to run. And so that comparison, 37 minutes to 26 minutes, that is an improvement of about 28%. Now we're going to do a failover simulation. So you can think of like any type of failover scenario or availability. And to just simulate this, all I'm going to do is take a couple of databases. I'm going to set it offline and then online again. Okay. In the first scenario, it took 2 minutes and 21 seconds. In the second scenario, it took just over 2 seconds to do, 2.4 seconds to complete. That's a 98% improvement between the serial scan and the parallel scan for the buffer pool. How about a file operation, right? So I'm going to do an alter database. I'm going to add a file. I'm going to remove a file, and then I'm going to drop one of those smaller databases. So in the first example, for a serial scan, it took 25 seconds, almost 26 seconds. In the parallel scan, it just took 1.6 seconds. So that's an improvement of about 93%. Okay, so you can see how these scenarios are way more efficient in SQL Server 2022. So we mentioned in the slides talking about how you can use extended events to monitor. So let's examine some of these scenarios. So I created an extended event session and I started it. And then I said, watch live data. Okay. Now, a whole bunch of the scenarios that I had before, okay, this time I'm going to do a parallel scan and then do a serial scan. And just so you can see, these are all these scripts that basically all the stuff that I was running before, right? I just did it all at once. Okay. So I did a parallel scan and then a serial scan of a number of different scenarios. Okay. That would cause me to have to scan the buffer pool. And when I watched the live extended event, we can see here that the buffer pool parallel scan, you can see the parallel tasks working for us. Okay. And you can see how the elapsed time is way lower for the parallel scan versus the serial scan where there's no parallel tasks helping me out. And you can see how much greater the elapsed time is for the serial scan. And again, this is on by default. You don't have to do anything other than get to SQL Server 2022 to be able to take advantage of this situation. Now, remember what you can do on other machines, older machines, SQL Server 2016, SP3 and up. You might want to take a look at the error log and look for these scenarios where we can see scans that take longer than 10 seconds to run. This will give you an idea for those larger boxes where you could potentially get some benefit by going to SQL Server 2022. So this is a good thing to start scanning already to try to get an idea of where SQL Server 2022 could help us with buffer pool scan operations. All right, let's review the in-memory feature family up until this point. So the concept of an in-memory database system refers to a database system that has been designed to take advantage of larger memory capacities available on modern database systems. An in-memory database may be relational or non-relational in nature. It is often assumed that the performance advantages of an in-memory database system are mostly owing to it being faster to access data that is resident in memory rather than data that is sitting on even the fastest available disk subsystem. However, many SQL Server workloads can fit their entire working set in available memory. So many in-memory database systems can persist data to disk, and it may not always be able to fit the entire data set in available memory. A fast, volatile cache that fronts a considerably slower but durable media, this has been predominant for relational database workloads for a long time. So it necessitates a really particular approach to workload management. The opportunities presented by faster memory transfer rates, greater capacity, or even persistent memory facilitates the development of new features and technologies that can spur new approaches to relational database workload management. So, looking at our list, we can see that the first three are independent of persistent memory. These first three are separate memory-based technologies. The first two are software constructs for SQL Server that when data is considered in memory, we are going to optimize concurrent access. This could be Hackathon, also known as in-memory OLTP, or this could be memory optimized TempDB metadata. I'll cover the memory optimized TempDB metadata improvement in detail. This is in the SQL Server 2022 TempDB, the uncontended system page latch concurrency enhancements talk. I have that session at DPS, especially if you want to get into TempDB deep dive. Definitely recommend checking that out. But I'll cover the in-memory OLTP improvements for SQL Server 2022 in the next slide. The memory protection keys, MPK, this is an Intel-specific technology used to guard against corruption by adding read-write access protection bits when working with memory mapped files. So in SQL Server, we use this MPK to decrease the risk of corruption, making its way to the database files residing on persistent memory. Presently, this is a Linux only feature. For the bottom three on the list, this is the persisted log buffer, also known as the tail of the log caching, data and file enlightenment, and hybrid buffer pool. This is we're gonna discuss these improvements together. So look at this as a foundation to build on. We're not going to say that you're going to get a specific performance result using these features. It can certainly help. We should look at all of this at the in-memory features as a foundation to build on. All right, let's first do an overview of in-memory OLTP. In-memory OLTP was first available in SQL Server 2014 and provides great performance gains for specific workloads. Some workloads can get up to a 30 times performance improvement in some scenarios, but again, it all depends on the workload. In-memory OLTP improves performance of transactional processing through a number of improvements. First, through data access and transactional execution efficiencies, and secondly, by removing lock and latch contention on the executing transactions. So in-memory OLTP isn't fast because it's in memory only. The speed comes from optimization of the data being in memory. Core components were redesigned to provide this optimized transactional processing with data storage changes, data access changes, and processing changes were redesigned to take advantage of the enhancements with in-memory computing. There are some key usage scenarios for in-memory OLTP, as in-memory OLTP isn't suitable for all workloads. It's generally best for those high throughput transactional processing applications that support large volumes of individual transactions with the need for consistently low latencies. So examples of this would be like financial trading, sports betting, mobile gaming, ad delivery, and scenarios like that. There are other usage examples such as data ingestion scenarios and caching in session state. We also use this technology for the memory optimized TempDB metadata improvement in SQL Server 2019. This is designed to remove bottlenecks for TempDB heavy workloads that had contention bottlenecks on the system tables. So in SQL Server 2019, the system tables involved in managing temporary table metadata can be moved into these latch-free, non-durable, memory optimized tables by leveraging in-memory OLTP capabilities. The memory optimized metadata improvement in TempDB is basically a combination of in-memory OLTP and temp table metadata features. So we took those system tables and the TempDB system tables and we moved those into these non-durable memory optimized tables. Now, while these improvements helped a lot of workloads, we also saw some memory related issues, especially for the memory optimized metadata improvement for TempDB. So memory usage for some memory consumers wouldn't shrink. That was one of the issues. It wouldn't shrink unless SQL Server process is restarted, and then the unused memory wouldn't get released even when workloads stopped running. So to solve for these issues, we made a number of improvements in SQL Server 2022 for several key areas. First, we improved supportability to give more insights on memory usage consumers and the DMV DM XTP system memory consumers has been extended to surface this information. Memory management has been improved to make it easier to reduce memory used by these memory consumers with minimal impact on overall performance. And we release as much memory as possible in case of memory pressure, and additionally provide customers with a method to release unused memory on demand with the SPXTP force GC stored procedure. All right, let's talk about persistent memory in SQL Server. So this is a quick diagram of what SQL Server can do to take advantage of persistent memory and where the opportunities lie. So first scenario is a block device. You could say I'm going to configure this and it's just going to be a drive. So in SQL Server code, we have no idea that this is persistent memory. For us, at the API level, this looks just like drive storage for this particular scenario. So why is this valuable? With the purchase of larger persistent memory devices, we can place our data files on technology that performs seeks within a single digit microsecond on advanced NVMe and persistent memory devices. Plus, this situation will support any version of SQL Server 2014 and above. The other scenario is the persistent log with log cache, also known as the tail of the log scenario. So this was introduced in SQL Server 2016, and it should be noted that Hackathon is what drove us to work on this. So if you use a Hackathon-based application with OLTP, the bottleneck became the transaction log. But why? So Microsoft was doing testing with in-memory OLTP to see how fast we could get with non-latching and non-spin locks, and we started noticing write log waits. Because even with in-memory OLTP, that's a persisted to an in-memory OLTP table, we have to write to the log. So now the bottleneck is the transaction log. This is where the persisted memory came in. The transaction log has multiple buffers. So we take log transactions, put them in buffers in memory, and then based on policies for commit operations, lazy writes, and so forth, we write that to disk. Now, it could be in NVMe SSD or other storage, but there's a process there that when you say commit to SQL Server, we take what is in the buffer and flush it to durable media, such as a hard drive. So what if we knew the log cache was on persisted memory? So if we know this, we know it's persisted. When we say commit, well, it's already committed in the cache. So we can save a lot of work ending at the commit. And now all of a sudden, your Hackathon transactions went from milliseconds of latency in the logs to just under 1 millisecond of latency. And this is the tail of the log technology, and it's been around since SQL Server 2016. Enlightened I/O. This is all about how SQL Server storage I/O can bypass the OS kernel I/O stack and therefore minimize the number of context switches happening between the user space in which SQL Server lives and the kernel space that is the domain of the OS I/O driver. So how do we cut down on all of this expensive CPU context switching for storage? Well, as you know, we are all about memory in SQL Server, buffer pools, log caches, and all this stuff. Persistent memory lets us treat the data files residing on these advanced storage devices like they are in memory. Essentially, I/O can become a simple mem copy operation. SQL Server automatically recognizes persistent memory as available so that you can enable some of these great PMEM-based features very easily. So we call this enlightened I/O or fast I/O because we're able to bypass the kernel and most importantly, avoid the latency of these instructions. Because it's doing I/O operations and kernel transitions back and forth, which leads to an improvement by avoiding the kernel transitions. So all we did is use a persisted memory storage via DAX mode. This is also known as direct access, and it's a special file system extension for PMM devices. What we're doing is taking advantage of this, and we're putting our data files on storage, and because of this, we're suddenly faster. So this was previously only available on Linux, but now with Windows Server 2022, we also support a similar functionality to Enlightened I/O through the regular Windows API. So if you're going to use Windows Server, we strongly recommend using Windows Server 2022 to get persistent memory support on SQL Server 2022. All right, so now hybrid buffer pool. So the engineering team knows the buffer pool really, really well. We've been working on this code for a very long time. And you probably have heard of buffer pool extensions on SSD drives. So what if we could take the same concept and say if it's persisted memory, then it's just like memory? But what if we could take the buffer pool array, just like the extension code, and map part of the array to that? So now if you're going to access your database, there's no such thing as really as a is a cold cache. Essentially, we're just going to go after the buffer pool, and it doesn't matter if it's the DRAM or persisted memory RAM. It just looks like one big buffer pool RAM to us, and this is why we call it the hybrid buffer pool. Now, keep in mind that persisted memory or even SLC-based NVMe SSD devices will always be somewhat slower than DRAM modules, but they are still really, really fast. Definitely, they're considerably faster than the standard QLC or TLC-based NVMe SSD drives that you're used to. You also don't have to do these 8K transfers as we discussed. If you want just one cache line, most of the time, you are going to be asking, is this the page I'm looking for? We look at the header and then we find the row, and if it's not there, we're going to go to the next page and so forth. So we just look at a few cache lines and then move on to the next page if we need to. So to compensate for the slightly slower cache read times, Hybrid Buffer Pool has an enhanced read caching capability enabled by default. This is where the hottest pages are promoted from persistent memory buffer pool to DRAM-based buffer pool. So with SQL Server 2022, we've added awareness of the persisted log buffer data to the hybrid buffer pool. We call this aspect of the hybrid buffer pool direct write. We call it direct write rather than performing copies of modified data pages from the persisted log buffer to DRAM. And then we have this checkpoint or the lazy writer write this back out to persistent memory, and we eliminate the unnecessary copy operations to DRAM and have the hybrid buffer pool modify data pages directly on persistent memory. So remember, because our log buffer is durable in this scenario, this is the perfectly safe thing to do. Direct write is the default behavior in SQL Server 2022 when both hybrid buffer pool and persisted log buffer are enabled. In our testing, performance gains of 30% or more were achieved just by using hybrid buffer pool for clean pages was observed for both analytical and operational workloads. So how do we enable? We use an alter command. If you have one of these persistent memory drives where you put your database files, you can use an alter server command for both Windows and Linux, and we enable the hybrid buffer pool. This is one of those foundational scenarios that we have with SQL Server. All of these cases shown on the slide, there are no application changes. We don't want you to have to touch the application. You may have to make a configuration change or change SQL Server BIOS or operating system configuration, but you should never have to really change your application. Your application is just going to get way faster by using this technology. Just note that the hybrid buffer pool is only for the buffer pool. It doesn't affect Hekaton or any other memory store. In summary, there's a 15% relative improvement in workload performance, primarily due to the reduction of CPU instructions by doing all of the work in the user space and cutting down the call stack of the kernel I/O. It is important to realize that this is not really a SQL Server feature. It's all about the path that is taken to open data through the kernel. It is the underlying platform that maps these files, which is very transparent to SQL Server. In fact, SQL Server is not even aware of it. And in SQL Server 2022 and with Windows Server 2022, we've brought parity between Windows and Linux in this space. All right, let's talk column store indexing and improvements here. So column store indexes were first made available in SQL Server 2012 and have been improved in every SQL Server release. Basically, a column store index is a technology for storing, retrieving, and managing data by using a column data format. So the use case for column store indexing is pretty straightforward. You need to return results over a large range of data, especially those expensive queries with a lot of aggregations and so forth, your typical analytics type of query. Then you have a strong use case for column store indexing. And there are additional use cases over the past releases, such as real-time analytics. But I'd say still the most common use case is querying against those large data warehousing fact tables and heavy reporting environments with a large aggregation and expensive type of query. So how does column store indexing provide better performance? The performance improvements comes from the columnar-based data storage and query processing that can be achieved with data compression. And since data warehouse environments tend to have similar repetitive values, grouping this data with high compression rates helps eliminate I/O bottlenecks in your environment, and memory overhead is reduced significantly. The result is that query performance will improve as SQL Server performs data operations in memory, batch executions in parallel, which will improve query performance, and column store indexing also helps by processing many rows together. So, how does it work? To achieve high performance and improve compression rates, the column store index breaks the table down into row groups. A row group is a group of rows that are compressed into a column store format. Then SQL Server compresses each row group into a column-wise fashion. When querying this compressed data, SQL Server accesses and retrieves only the data that is needed using the metadata for fast elimination of column segments and fast elimination of row groups without even having to read the data itself. So we can have a clustered column store index and a non-clustered column store index. A clustered column store index physically stores the entire table, and to be sure, a non-clustered column store index and a clustered column store index really function the same way. The difference is that a non-clustered column store index is a secondary index that's created on a row store table, and a clustered column store index is the primary storage for the entire table. Now, we recommend using a clustered column store index for data warehouse scenarios with large fact tables and large dimension tables. We recommend using a non-clustered column store index for real-time operational analytics and for scenarios where you need a specific index to improve reporting against like an OLTP environment. Okay, so what's new in SQL Server 2022? Beginning with SQL Server 2022, ordered clustered column store indexes can improve performance for queries based on an ordered column predicate. The ordered cluster column store index sorts the data in memory before the index builder compresses the data into index segments. This has the potential of more efficient segment elimination, resulting in better performance as the number of segments to read from disk will be reduced. Additionally, in SQL Server 2022, all column store indexes will benefit from an enhanced segment elimination by data type. Segment elimination historically applied to numeric, date, and time data types, but beginning in SQL Server 2022, segment elimination capabilities extend to string, binary, and GUID data types. Now, regarding the Advanced Vector Extensions 512 extension, we've added support for hardware that can improve column store performance. So Microsoft has studied numerous data layouts associated with column store and CPU instructions required to process data. Various algorithms have been optimized through the column store codebase. SQL Server started to take advantage of vector-based hardware with the release of SQL Server 2016. And in SQL Server 2022, we've enhanced this capability with added support for the AVX 512 extension. When compressing, building dictionaries, and processing data in batch mode, a vector design is leveraged, and SQL Server can detect the level of CPU support when supported capabilities are discovered. SQL Server will take advantage of this hardware scalability and performance capabilities. Simply put, in SQL Server 2022, we have much better segment elimination through ordered clustered column store indexes, improved segment elimination through data type support, and increased optimization support depending on the underlying hardware. All right, so we have just a couple more quick topics to cover. Let's first talk about XML compression. The XML data type was introduced in SQL Server 2005, and as a result, the XML data type has become a common data type that's used to store unstructured data in SQL Server. The challenge, however, is when customers rely on this data type, they often store large amounts of data. Customers such as banking, legal, healthcare all store XML data for longer time frames, which can drive up capacity and increase storage costs. So the data compression option in previous versions of SQL Server did not help with compressing XML data types, as XML data type is stored off row and data compression only operates with in row pages. So in SQL Server 2022, XML compression for data and XML indexes will allow customers to reduce their storage footprint without any driver updates or any other changes needed to the applications. The primary intent of this improvement is to achieve space savings, space capacity improvements, but you may also see some IO performance improvements for certain workloads. All right, our last topic is shrink database with low priority. As a general practice, we do not recommend shrinking database files because they will usually reclaim the space on general usage. However, there are many customers that do need to shrink their database files, especially after regular cleanup operations, post or archival projects. This could be due to localized ETL or temporary reporting objects. There's also customer databases that are application created as well. Applications that create database per user or per customer may use a model or a template with some sort of operation that creates user objects. This is definitely the case for hosted environments. This can all drive database space. So it's often stated otherwise, but storage is really not cheap. And with the increasing amount of data that needs to be kept for compliance reasons, customers are looking for any way that they can manage and reduce their storage footprint. But unfortunately, on SQL Server 2019 and previous versions of SQL Server, the shrink database command could lead to blocking and lock waits, especially with active maintenance such as managing indexes and other scenarios on busy active SQL environments. So as a result, customers had to wait and schedule their shrink database and data file maintenance operations to after hours, as any long running reader operations essentially made it impossible to shrink data files during regular business hours. So the shrink database wait at low priority feature addresses this problem by improving shrinking when using this mode. This allows readers needing a schema stability lock to not be blocked by the waiting shrink command. Using shrink database at low priority does not affect customer workloads. The only expense is delaying the shrink operations. So here we can see an example of using DBCC shrink file with wait at low priority. So in summary, the benefit is being able to shrink database files without concurrency conflicts, and for some environments, giving customers strong capacity savings. As you can see, we've had a lot of great improvements with SQL Server 2022 in the areas of built-in performance, scalability, and management. In part two, Kevin Farley will go into availability and recovery improvements in SQL Server 2022. Thank you so much for watching, and thank you to the data platform geeks and SQL Server geeks. And one last thing, you can win some prizes by posting your selfie with hashtag DPS2022. Please give session feedback and visit the sponsors. And don't forget to follow the Data Geeks and Data AI Summit on Twitter. And please follow me at Pless for the latest on the SQL Server 2022 release and storage engine topics. Much thanks, everyone.